My name is William Hahn, and today I would like to discuss some research I've been working on with Vinod Rimal in the area of compressed topological data analysis. So briefly, we'll discuss some of the ideas in TDA, particularly the notion of persistence and persistence entropy. And then we will describe a simple toy problem that we have developed to look at how we can apply random projections to our point cloud. And then we show how the topological data analysis techniques still apply even in this compressed domain, and we will demonstrate this with a brief tutorial. So as you're well aware, we can create our persistence diagrams by creating a disk graph around each of our data points, and then growing the disk as a function of epsilon, and then look at the emergence and death of different topological and graph structures as we change this epsilon size. In particular, we have the barcode formulation, which will allow us a representation of the birth and death of these different structures as epsilon changes. And it's this diagram that we're going to be using to calculate our entropy, which is essentially going to measure how different the bars of the barcode were in length. And this value is going to be the feature that we're going to use to send to a simple classifier, and then we will apply it with the compressed space. So to take some ideas from signal processing and harmonic analysis, we can think about how data is stored as a JPEG. And typically what happens is something like your camera phone is going to remove 99%, 95% of the data when it creates a JPEG. And so when you send a photograph to someone over the telephone, the photograph that other person gets is not the same photograph, but they can't tell the difference. But this seems rather wasteful. If we're going to calculate all these samples just to throw them away, can we acquire them more directly? And so this is the idea of compressive sensing. How we can exploit this low-dimensional structure, that often we want to recover the full data, but in general, we don't necessarily have to do that. We can just detect or classify or estimate something about our signal of interest. In our case, is going to be our point clouds. So we want to think about the geometry of sparse signals where many of the dimensions are going to be 0. And that gives us a very interesting set of properties that we can take advantage of. Particularly when we have a sparse signal, we can apply a random projection to a lower dimensional embedding space. And we know from the Johnson-Lindenstrauss lemma that these point cloud embeddings will be preserved. Their approximate length of the vectors and the approximate distance from any pairwise set of these will be approximately preserved. And so this is known as the restricted isometry property. And under certain conditions, we have it that, and we map these vectors, that we're not going to change the pairwise distances very much. And so this is what we've been exploring to see, will the topological data analysis still work in this setting? And so we've had for a long time, the Shannon Nyquist theorem, but really this was a pessimistic sort of sampling, that if we sample randomly, we can actually get away with a lot more, or a lot fewer samples rather, and still recover the signal. And so this is the idea of how much can we reduce the dimension of our point cloud and still process. As you're aware, the algorithms that are typically used are sensitive to the number of points that are being processed. So if we can reduce the number of points, that will speed up and make a lot of these very practical. And so as an example of this, we can think of having a sparse vector x, and then we're going to multiply it by our random matrix here, and then we're going to get a smaller vector y that's going to only have m numbers as opposed to n. And so now this is the idea of what we're going to do with our point clouds. We're going to assume they're sparse in some basis. What's nice about the random projections is it's universal. You don't have to know what basis it's particularly sparse in. And since we're not interested in recovery in this case, but rather classification of the point cloud into one of two different types, then we don't need to know the basis that it's sparse in. And we can just use a random matrix to do the dimensionality reduction. So just as a visualization of that there, we have on the right a sparse vector and then a random matrix, and then we can see our compressed vector. And so we can imagine doing this to our point clouds, our vectors in Rn. And so as the number of measurements increases, we're going to get our error drop, but then we're going to look at the end to see how much we can push that down to reduce the number of measurements as much as possible. The measurements here are sort of equally unimportant. Losing a few doesn't really matter, so we can almost shuffle them around. Sometimes these are called holographic in the sense that the information sort of comes from everywhere. It's a mixture of everything. And so therefore, it's nice for error correcting. And if there's a situation where maybe this data might need to be transmitted somewhere before it's processed, if some of these measurements are lost, then that's not really critical, which would not be the case in a regular point cloud because some of the points could be more important, essentially. And so what we're going to be interested in is can we run our TDA algorithms directly on these compressed measurements? And so now what we would like to do is show you some of the code that we've been working on so that you can try these experiments yourself. So we are working in Python. We're using Jupyter Notebooks. And so we're using a package called GTDA. And this allows us to create and calculate RIP's persistence as well as the persistence entropy. We're going to be using scikit-learn to import a very simple random forest classifier for our experiment. And then we're going to import also a simple split to separate our training and testing data. And then a couple libraries for plotting and, of course, Numpy. And then here you see Tata Sets, which is a tool that will enable us to create our artificial toy data set consisting of spheres and torus. So here we set the number of points that we would like in each point cloud. We set the ambient dimension, so in this case R90, and then we can set the number of examples that we would like generated, in this case 500. So then we use Tata Sets to create these torus and embed them in the ambient dimension of R90, and then we can see here it will automatically plot the first few coordinates of that for us as a point cloud. And here we see it creating a sphere. So we can set the radius, and again, we're setting the ambient dimension and the number of points we want. And so what we're going to do is we're going to create 500 of these. So we'll have 1,000 in total in our data set. And so we can create, in Numpy, we'll create some empty array. We'll have the number of examples, and then the number of data points, and then the number of ambient dimension. And we're going to do that for both the torus and the sphere. We can initially put in noise, but then that's something you can add. Then what we'll do is we'll loop through the number of examples and generate each one of our point clouds and store those in our array there. And then we can create labels for our classifier. And so we'll classify the torus and the sphere. We can then create an object that will create our RIP's persistence. And then we can send our point clouds through the fit transform, which will create our diagrams, which are stored in the Numpy array. We can then create a persistence entropy object and then calculate from the fit transforms from the diagrams the features of the persistence entropy. These are going to be our inputs into our random forest classifier. And what we're going to be looking at is how these features and the classification performance changes under the random projection. So here we're going to split our features into a training and testing set as well as the labels. So we'll have the X train and the Y train as well as the validation set X and Y. We're going to use our random classifier and create a model. Then we're going to fit that model using the training data and then evaluate that model, score it using the validation data. So in this case, it's a very easy problem, and we can get 99.99% very easily. What we're now going to do is randomly project our point clouds down to a dimension in R50. So we're going from R90 down to R50 randomly. So we're just going to create a random matrix with rand n, so normally distributed, and then we're going to add a sort of dummy index here with the none. That will create a sort of a 3D array here. So we have our point clouds, or point cloud shape. We have 1,000 of them. There's 100 points in each point cloud, and they're in R90 originally. our compression matrix WC is going to have one of them. That dummy dimension will help the batch multiplication go correctly. Then we can see it has R90, and that's going to map this to R50. So we do a simple matrix multiplication to multiply our point cloud with our compression matrix, and that's going to give us our compressed point clouds. We can see the shape of them is going to be 1000 by 100, now by 50. Now we're going to run the same classifier again to see how well it can do in this new space. So again, just as before, we're going to create our RIPS persistence. We're now going to run our compressed version of the point clouds. That's going to create our diagrams. We are then going to calculate the entropy from the diagrams to calculate our features. We're then going to split our features and labels, and again, train our random classifier. We're going to fit it on the training data and then score it on the validation data. And so here you can see that we also get 99.6. So now what we've done is, so we've seen here that there's really not much change in the performance of this classifier for this very simple task from going from R90 to R50. So now we've made a simple loop here, where what we're going to do is we're going to go from just one single measurement all the way up to 31, which is an arbitrary stopping point. And then for each time, we're going to calculate a random matrix. We're going to multiply that by our point cloud to create our compressed point cloud. That's going to then use that to create our diagrams. Our diagrams are then going to be used to calculate our persistence entropy features. The features are going to be split into training and validation data. We're going to initialize a random forest classifier and again fit the model with the training data. We then again score the model with the validation data, and we will store the result in an array and print out the result. And so this is what we've found so far, is that as we compress this dimension, we get a, the classification accuracy holds very steady. There's a little noise because this is a random classifier. And so next we'll be repeating these to look at the variability. But what we can see here is that essentially this ability to classify the torus and the sphere really survives these random projections all the way down to very low dimensions, which it makes sense, right? Because these are rather low dimensional objects that we're embedding in a very high dimensional space. But this is very promising as we extend TDA to larger and larger data sets of different data types, and that we can now hopefully compress these very large point clouds into a smaller dimensional space, lower dimensional space, which will hopefully speed up the processing time that is required, but still, as we've seen here, as it suggests, preserve the ability to classify and identify these topological features in the data. So that is what Binod and I have been working on. So we thank you for your time today. If you have any questions, we will list our emails in the comments below. Thank you again for your time today.